Okay, we've learned what power functions are and we've learned what exponential functions are. In this video, we're going to learn how to determine the units of the constants that you find in a power function, and I'll show you how to determine what the correct units are for the constants found in an exponential function. First, we'll start with units in a power function. And a note, whenever we have an equation like this, F equals ma, and of course it's the net force, the unbalanced or the net force that equals m times a. For any equation like this, we can express units of net force using brackets. So the units of the force, the unbalanced force, are equal to the units of mass times the units of acceleration. And of course we know that's true because the units of F net is Newton, and 1 Newton is equal to a kilogram times a meter per second squared. So that's the first note about units. We express the units using brackets. Okay, so on to a power function. The general form for a power function is d, the dependent variable, is k, a constant, times the independent variable raised to the power of n, another constant. And the constants, again, are k and n. So whenever we do an experiment, we always know what the units of the dependent variable are. If your dependent variable is final velocity, it has units of meters per second. If your dependent variable is, I don't know, height, then it has units of meters. Likewise, we always know what the units are for the independent variable. But what about the constants? And that's what we're going to look at next. The first one is easy. This constant n is always just a number that has no units. The power n has no units. So n has no units. And the reason it has no units is because exponents can't have units. Alright then. What about k? What are the units of k? K has units equal to or of the units of d divided by the units of I to the n. So I've just given you the answer right there. I'm next going to show an example. First I'll prove this on the next slide, then I'll show an example of this. So again, here's our power function. D is k times I to the n. Now we can put brackets around everything. So the units of d are equal to the units of k, the constant, times the units of I to the power of n. And if we isolate the units of k, which we do by dividing both sides by the units of I to the n, we get this. And this is exactly what I wrote on the previous slide. Alright, let's see an example. You do an experiment where you take a ball, right, and you hit it up into the air with your hand, and you have some way of measuring the force that your hand exerts on the ball. And what you do is you change the force on the ball in different trials. And in each trial, based on the different force the ball receives, the different upward force, it takes a different amount of time for the ball to make 12 bounces, right? And so in the first trial, you hit it up with a particular force, the ball goes up, it goes down, it bounces 12 times, and you record how much time passed for that to occur. Then you hit it up with a different force, you count till it reaches 12 bounces, and you measure the total time for that whole process to occur. And what you find is that the time t is equal to some constant, 18.3, I made that number up, times the force to the power of 1.5, like that. Or maybe it's not even a round value. Let's say it's the power of 1.2, something weird. So what are the units of the constant? We know what the values of the constants are. N is 1.2, K is 18.3. N we know has no units, but what are the units for 18.3? Well, to figure it out, here's what we're going to do. The units of K, in this case, are equal to the units of T, and it's going to be divided by the units of F. First, let me write this. I've taken my equation with the constants plugged in, and I put brackets around everything. So what are the units of time? Let's fill in the left side. The unit of time is second. Units of K are the unknown. And what are the units of force to the 1.2 power? It's easy. Newtons to the power of 1.2. So if you divide both sides by newtons to the 1.2, then you get the units of K are seconds times newtons to the negative 1.2. Or if you prefer, you could write seconds divided by newtons to the 1.2. So you could either use negative in the exponent, or you can put the newtons to the 1.2 in the denominator of a fraction. So that's how you find the units of K. Okay, so the last thing is quicker and easier. This last thing is units in an exponential function. And it works out the same regardless of whether you have positive growth or negative growth. So I'll just use positive growth as an example. The general equation for positive growth is d, the dependent variable, equals d sub 0. Actually, let's do negative growth. D equals d sub 0 times e, Euler's number, to the negative lambda I, where I is the independent variable. And your constants are d sub 0, so d0, e, and lambda. Those are the constants. My t looked like an F. Let's try again. Okay. So what are the rules for units? They're really, really easy. D0 always has the same units as D, the dependent variable. E never has any units. In fact, you never even put the value of E. We always leave it as E when we write our equation. So you never do what I'm about to do. You never do, what is it? What's the value of E? 1.2 something. That's probably wrong. Times negative lambda I. You don't do that. That's wrong. You just leave this here as E. And lastly, what about lambda, the decay constant or growth constant? That's easy. Lambda always has units of 1 over your independent variable. So whatever the units of the independent variable are, you invert them to get the units of lambda. And those are your 3 simple rules. Let's see one quick example. Okay, here's my example of exponential decay. Let's say I have a cup, and in that cup there's 50 milliliters of milk, and I add to it 10 milliliters of syrup. I mix it up with the milk, then I take the whole solution and I pour it down a ramp with edges like walls so that it doesn't spill out the side. I pour it down, it flows down, and then when it gets to the bottom, I measure how fast is it going. I measure that. In the next trial, I add, instead of 10 milliliters to the solution, or to the milk, I mix with the milk 20 milliliters of syrup. And I keep going in this fashion. Okay. And so my independent variable is the volume of syrup. Volume of syrup is my independent variable. My dependent variable is the speed at the bottom of the ramp. Okay, volume big V and speed little v. And what I find is that the speed little v is equal to some initial speed value when there's no syrup in the milk, times e to the negative lambda, and what's my independent variable? It's volume, big V. And I do some data collection, and from my analysis of the data, I discover that VO is 1.9, let's say. No, how about something bigger? VO is 15.7, and lambda, I discover, is 0.014. So I have to find what are the units of V sub 0, 15.7, and what are the units of lambda? Well, imagine that we set big V, the volume, to 0. When there is no syrup at all, I have negative 0.014 times 0, which gives me e to the 0, and e to the 0 is, of course, 1. So I could rewrite this equation as 15.7. But that's a speed. That's the speed when V, big V, the volume of syrup, is equal to 0. So if 15.7 is a speed, it needs units of meters per second. So I'm going to erase some of this stuff. And that means we can come back into the original equation that I wrote above. And I can put beside 15.7 the correct units, meters per second. What about lambda? What are the units for lambda? Negative 0.014. Well, any exponent, including this exponent right here, has to have no units on the whole. So when I multiply everything out, it can't have any units. Which means that the units of lambda times the units of volume equals 1, something with no units. So, okay then, lambda times, what are the units of volume? Milliliters, equals 1. And that tells me, if I divide both sides by milliliters, lambda is 1 over a milliliter, or a milliliter to the negative 1. Okay, so I can come over here, back to the equation, back over here, and I can fill in milliliters to the negative 1 for lambda. And that's the unit of lambda times volume. So there's an example where we solved for the correct units of d sub 0, the independent variable's initial value, which in this case was the initial speed, or the speed when the volume, the independent variable, is 0. And then I solved for the units of lambda.